Hello everybody. Today we're going to continue with our review of operational amplifiers. Specifically, we're going to delve into what we call the ideal op-amp model. I'm Michel Naharvez.
And I'm Vivek Subramanian. Let's get started. We're going to introduce a concept now that's very powerful to simplify analysis of op-amp based circuits. And in particular, we're going to introduce this idea of something called an ideal op-amp. So let's think about our original amplifier that we started with, which we covered in the last module. And when we think about this, we define certain characteristics that would make an amplifier essentially ideal. And those were, first, on the input side, there would be no currents going into the input, so they would essentially be infinitely resistive looking into the inputs. The output would have zero output resistance, and that would then allow us to have essentially no currents going in and no load dependence on the output.
So think back to the non-ideal model we've already given you. And if you recall there, not only did we mention that in realistic or existing good quality op-amps, we had a very high input resistance and a very low output resistance. I think it's also worthwhile at this point to go back and review what the voltage dividers would be at the input and the output in the cases where the input resistance is infinite and the output resistance is zero. And you'll find that it simplifies greatly because all of the input voltage gets carried into the amplifier, and likewise all of the output voltage of the op-amp is presented to the load.
So Michel, if I understand correctly, what you're saying is no matter what my source resistance plugged into VP is, I'll still get the full VP at the input to the op-amp because there's no resistive loss inside the op-amp.
That's right. Effectively, you're resistively dividing with an infinite resistance, and so it all drops across there. And if you don't panic if you don't quite remember. If you just go back to the previous lecture notes, you'll see that we did that, and just ask yourself what would happen for an input of infinity and an output of zero for an op-amp.
Okay, so at this point what we've done is we've introduced our first important outcome of this ideal op-amp assumption. In other words, we assume that the currents going into the inputs, that is IP, the current going into the non-inverting input, and IN, the current going into the inverting input, are both equal to zero. Now, what you're going to see is we are going to make an important consequence out of this assumption in the case where we have feedback. And specifically, you're going to see a situation where VP will be equal to VN. And you'll see that when we actually include feedback. So this second constraint over here, just bear in mind for a second. But what's going to get us to the second constraint is really another important assumption. And that is we assume that the gain of the amplifiers is infinite. In other words, the voltage gain for this amplifier is infinity. We've got the input resistance is infinity and the output resistance is zero. So basically what we have are these three assumptions. A is equal to infinity, Ri is equal to infinity, and Ro is equal to zero.
So this is a good point to go back to what Vivek was just saying about the voltage constraint. And we're going to come back to this several times in this module to make sure no one makes mistakes. This model is intended to be used when the operational amplifier is wired up in a negative feedback configuration. So this little diagram here, in fact, hasn't included that. We're assuming that about the circuit inside the triangle. You'll see it when we do the explicit examples, but make sure you don't mess that up. The reason you get that VP equals VN, that we assume that, is because we are going to wire it up into negative feedback, and that's a consequence of it. And we'll explain it as we go along. But that's very crucial. The other thing I want to point out is I find that students get the current constraint and the voltage constraint, that it bothers them that both of them are in effect at the same time. It's just something that seems very non-intuitive. And all I would say is, for the moment, just take it as a mathematical axiom, and as we work through, we'll give you the intuition for why the approximation gives us these rules.
Now, what are we going to do with this? Well, we'll basically use our standard nodal analysis techniques, but life is going to become easier because of a consequence of these rules. And we call these the so-called golden rules with respect to ideal op-amps, and that is, in the case where we use this in a feedback configuration, and specifically a negative feedback configuration, we will always assume that because of this very high gain of the amplifier, it'll make sure that VP is equal to VN. And further, it'll make sure that there's no current going in to the amplifier. In other words, IP is equal to IN is equal to zero. What this is going to do is it's going to simplify our nodal analysis greatly. And also a consequence of having zero output resistance is doing the output calculations of current will be much, much easier because we don't have to worry about an internal resistance on the output.
Right. Last thing to point out, do not try to do KCL at the op-amp output. when you're using the ideal op-amp model, you just flat out don't do it. And that's because you have no idea what current's coming out of that back end. It's an unrealistic situation. So you just learn, you never apply KCL at the op-amp.
Right, and the reason for that is because the output resistance is 0.
That's right.
So,
okay, so let's take an example. I think the best way to learn this, and most of the module is just a series of examples where we can go through the math. So what we've done here is we've taken an op-amp, we have wired it up in a particular configuration. If you remember your previous module slides, you might recognize this as a non-inverting amplifier, but if you don't, that's also okay.
if you look at this, the first thing you're going to note is it is wired. Let's do our test. Is this wired in a negative feedback configuration? Well, I see the output has a connection back to the input. So therefore, indeed, it is in a negative feedback configuration. So maybe this is a good candidate for using our ideal op-amp model.
Yeah, that's right. So how have we wired it up? We've got a realistic source with its ideal voltage source and its source resistance coming into the non-inverting input terminal. We've got the output going through a resistor and then back to the inverting input terminal, and then we've got this second resistor goes to ground. We know off the bat, we've been told we shouldn't do KCL at this node. That does not preclude us from trying to do KCL at this node here and applying the golden rules. So let's go ahead and do that, and you'll see how easy it is to solve these op-amp models. So first thing we know, we have our first rule, which is VP must be at the same potential as VN. And notice there's another consequence here. Because Vn and Vp are at the same potential, and we know from our second golden rule that Ip equals 0, there can be no current going in, that must mean there's no current going through Rs. If there's no current going through Rs, what do we know about that voltage drop?
Well, then we know that there's no voltage drop across Rs, which means Vp is equal to Vn is equal to Vs.
Vs. Okay? So we've got this first observation. Now we go look at node Vn. And as I sort of hinted, we can do a KCL at Vn. So Vn minus V out over R1 plus Vn over R2 equals 0.
I notice you didn't add another current component for that third branch, and the reason you didn't do that was because In is equal to 0.
That's right.
So you see here how the ideal op-amp simplified our analysis.
Right. And so we've done this, we've combined them, and we clean this up, and it's algebra. It's very easy to see that the output voltage is related to the input voltage by this fraction here. And so we know we've got the answer for our voltage amplification, right? We know the gain of this amplifier. It's R1 plus R2 over R2. We know it's non-inverting. And if you go back, and I'll do this in a second more explicitly, or Vivek will, you'll find that this is the sort of the simplified form of what would have happened if we used a non-ideal amplifier and solved out the entire set of equations.
Yep, that makes sense. And you'll notice, by the way, that this in fact gives you a gain which is defined purely by the resistors. You'll remember from the last module we said this is a big advantage of feedback. In fact, this topology is a standard topology called a non-inverting amplifier, and you can set the gain of the non-inverting amplifier purely by a choice of R1 and R2.
Yeah, one of the fun things to do once you get your ideal op-amp model down is to replace it with an non-ideal one, right? Put in an actual resistor here between the inverting and non-inverting terminals, as we did before, and put an output resistance at the output, and the gain, if it's not infinite, put a gain, a voltage source, dependent source, and try to solve the same topology. And we've done a couple for you already with the non-ideal case, but try to do it. And what you'll find is that you'll get a much more complex expression that includes the input and output terms and the gain term. But in the limit as that input, the open loop gain goes to infinity, and these resistances go to infinity and 0 respectively, you recover the ideal expression. And that's reflecting what we told you. In the limit as this amplifier behaves ideally, you get these simplified expressions that are a function only of the biasing resistors.
Of course, remember that you still do have the other constraints of the system. In other words, there's a limit to the voltage swing capability of this system.
That's right.
Okay.
Let's do another one.
All right, let's do an inverting amplifier.
You do this one, Vivek.
Okay, sounds like a plan. So let's do an inverting amplifier. So in an inverting amplifier, you'll remember that what we're doing is we are applying the source voltage that we're trying to amplify to the inverting terminal. We still have it wired in a negative feedback configuration. Therefore, this is a good candidate for using an ideal op-amp analysis. So let's proceed. All right, so let's go ahead and do the calculation at node Vn. So we will set this up, and we've got the current I1 is Vn minus Vs over Rs. The current on the feedback path is Vn minus V0 over Rf. And the current going in would be In. You know that if that, of course, is going to turn out to be 0. Okay, that's our first equation. Our second equation comes from the ideal op-amp assumption. In other words, Vn is equal to Vp, and Vn is equal to Vp will be equal to 0 because Vp is tied to ground.
Aha.
So we've got Vn is equal to Vp is equal to 0. So think about what I've done. From the ideal op-amp assumption, I've already been able to simplify this quite a bit. I can get rid of the In because there is no In. The Vn gets replaced by 0, and so what I'm going to end up with is an equation that has Vs, V0, Rs, and Rf.
So kind of what we expect. Let me ask you another question. So I've heard that sometimes people say that the inputs of amplifiers with feedback create a virtual ground at the input terminal. Is that what's going on here?
Yeah, that's effectively what we're treating this as, because what we've done is we've taken one input and we've tied it to ground, and the consequence of that is the other input effectively looks like it's at ground, and that's because of the very high gain.
So what you're saying is that the amplifier is using negative feedback to essentially close the difference between the voltages at the two input terminals, to reduce it so that effectively they're the same potential. It's fighting to do that constantly using the feedback loop, and thus it's keeping them clamped at ground because one of them is ground.
Yes, and there were two requirements for that to be true. First, we had to have a very high gain in the amplifier, and second, we had to have negative feedback.
Okay, that makes sense.
Okay, so then let's go ahead and put this together to define the gain. So we can solve these equations. Remember, the Vn's get replaced by zeros, and the In disappears. And so when we simplify this equation, we find quite simply that the gain is just calculated as VO over Vs, which is minus Rf over Rs. So you'll notice that again we've now got a system where we have an amplifier where the gain is set purely by the resistor elements, and because this is an inverting amplifier, you notice that there's a negative sign that shows up.
Awesome. Let's do another one. Let's keep going. Summing amplifier. So let's look at a case where we've got more than one source. Okay. So I'll tell you right off the bat, I like doing these types of problems by superposition, and it's a good exercise for you to remember to use superposition.
So if I remember right, Michelle, what you're saying with superposition is we could eliminate V2 and do the analysis with V1, and then eliminate V1 and do the analysis with V2, and then just put them together.
That's right. And since you've already learned and we've gone through that in quite some detail, I just thought I'd point out it'd be a good exercise here. We're not going to do it that way, but it'd be a good exercise to practice your superposition with this circuit. It's completely linear circuit, so it'll work well.
Now I'm going to look at this and take a guess. So you've got this hooked up to the inverting terminal, and so I'm guessing the output is going to be some sort of inverted function of the inputs?
That may well be. Let's take a look. And by the title, by the name of this thing, you can also imagine it's probably going to be some sort of sum of these things. So the way we're going to do it is we're going to source transform the two realistic input voltage sources, right? So just by looking at this, what you can see is that there are two realistic sources connected with their associated source resistances. Instead of calling them RS, we've called them R1 and R2, and you've got your two ideal voltage sources. We can take each of them, source transform them so that they're a current source with a parallel resistor. As you'll recall, the resistors keep their value, and the value of the current sources equals the original voltage source divided by that resistance. So this is a Norton equivalent circuit. Once we set them up this way, and notice the right side of this didn't change at all because that's just the amplifier configured with a single feedback resistor. Okay? But once we do this, we can put them together. So these currents, these two sources can be summed together, and the two resistors are in parallel. So you can take the parallel combination and then transform again.
So if I understand what you said I should do is, so R1 and R2 in parallel, so I'll combine them into one equivalent resistor, and since the two current sources are in parallel, I add those together.
That's right.
So I'll get a new current source, which is the sum of those two. I've now got a resistor that's an equivalent, and then I'll transform back into the Thevenin's form.
The Thevenin form. And the reason we've glossed through it is, we felt that at this point of the course, this is good exercise for you to make sure you can sit down and generate this on a piece of paper on your own. So you have the answer. You'd have the voltage source at the input is this expression, and you have your RS resistor here, and so and which is of course the equivalent, as Vivek said. So once you have this going, it's actually pretty straightforward because you've kind of seen this before. We can use the same golden rules now. It's just you have a sort of somewhat funky expression for the Vs, but that won't stop us. And what will happen if you do this, if we apply the golden rules, whoops, you will find that in fact you effectively have something that takes the V1 source and gives it a gain of RF over R1 and inverts it, so it's an inverting amplifier with a RF over R1 gain, and another inverting amplifier with an RF over R2 gain, and those two things are added to each other to give you the total gain.
Okay, now it's kind of interesting to look at this because I really see how easy this was by superposition.
That's right.
And I see how easy it was because this is essentially the calculation that would have resulted if I only had the V1 source, and this is the calculation that would have resulted if I only had the V2 source, and I'm just adding them together.
Right. And I think that's also the more intuitive way to look at this. I mean, let's think about what this is telling us, and then I'll rationalize why we did it this way. The reason superposition is so intuitive is what effectively is happening here is that the ratio of the feedback resistance to the source resistance of each of the inputs gives you the respective gain for that input. So as you just have two inverting amplifiers that are operating simultaneously, and because it's a linear circuit, superposition takes care of the rest. We did the example this way because it is a good way of getting used to using all of the other tools we've been teaching you in the context of this sort of new paradigm, which is the ideal op-amp model, and have you work out now, without knowing the superposition, force yourself to work out the golden rules and see that all of this math works out and you get the right answer. So I think it's a good exercise. Oop.
Okay. So, and the other thing to note about this is, of course, that the form that we finally ended up with was basically the inverting amplifier that we just looked at in the very last section.
Yeah, that's right.
Okay. Let's now move on to another version of an op-amp circuit, and specifically this is the difference amplifier. And the difference amplifier is the amplifier shown here, where you see that I've now got two sources, but one of them is applied to the inverting input and the other is applied to the non-inverting input. Again, there is a feedback configuration, so I am qualified effectively to use the ideal op-amp framework.
So let me jump in. What happens if, let's look at two other cases. What happens if they don't see any feedback configuration? Should they use the ideal op-amp model?
If you don't see feedback, you don't get to make the assumption that Vn is equal to Vp, so you wouldn't be able to use the ideal op-amp model.
So that's clear. And this one's a tricky one. What happens if, not us, but what happens if someone sneaky were to put an op-amp into positive feedback mode and throw a circuit at them with that in there?
Well, you'd still have the same problem. You don't get to make the assumption
you don't
that
get to
Vn
make
is
the
equal
assumption.
to Vp.
Yeah, so make sure you've got that clear. And Vivek and I in class will go through what happens if you put them in positive feedback mode. Okay, go ahead, Vivek. Sorry to interrupt.
All right, so let's go ahead and look at the circuit and let's proceed. Now, you can already get into it as to what's going to happen. I have V1 on the inverting input and V2 on the non-inverting input. If I were you, I would surely expect that these two will subtract in some way, shape, or form. So let's go ahead and set that up. So let's go ahead and do the analysis at the inverting input. So let's do a KCL at the inverting input. We have Vn minus V1 over R1, that's the current through this branch, plus Vn minus V0 over R2, plus In is equal to 0. Now remember, In is going to disappear. All right? Let's do the same calculation at Vp. And at Vp, what we can write is Vp minus V2 over R3 plus Vp over R4 plus Ip is equal to 0. So we've got basically two KCLs that we've set up now. And you'll remember that In and Ip are going to disappear. So to proceed, we will impose the ideal op-amp constraints. And the ideal op-amp constraints are twofold. First, In is equal to Ip is equal to 0, so those are going to disappear. And because we have negative feedback, Vn is equal to Vp. So now we can take these two simultaneous equations that have multiple unknowns, and we eliminate the In and Ip, and we can essentially replace Vn and Vp by each other, and then we can simplify these equations to get a simple linear equation relating VO to the inputs. And so it'll relate it to V1 and V2.
So what I find cool about the difference amplifier is, one, that again, each input voltage's gain expression comes from these resistance values relating to and in relation to the feedback resistor R2, right? And furthermore, and this one's a little subtler, but I encourage everybody to go back and think about it. Notice how this looks exactly like the inverting amplifier gain we saw before in the simple case of the inverting amplifier. You just get R2 over R1. And it's not a coincidence. If you were to kind of remove this and replace it with ground, this might look familiar, right? And again, this bottom branch right here has its own gain value that is non-inverting. So I would encourage you to actually take a look and see if you can intuitively see how the difference amplifier looks like previous simpler amplifiers that we just did, and then they just come together by the subtraction.
Now you can, again, this is a case where you could use superposition. Because think about the superposition case. In the superposition case where if you were evaluating with respect to V1, you would set V2 to 0.
That's right.
And then that means you've effectively grounded this side. And so that would give you this term over here. And then in the other case where you'd set V1 to 0, you'd get this term over here.
Yeah, that's exactly right. That's exactly right. So superposition is your friend when really trying to get some intuition out of these circuit topologies. And then, as we like to do, these are the actual gain functions for each of the two branches, and they're summed together. Of course, one is negative, and so you get what's called the difference amplifier. Okay? I also think this is nice. We'll come back to this much later when we start doing integrators and differentiators with op-amps. But you notice that you can obviously do simple analog processing. And long ago, before the advent of the modern digital computer, this was certainly the case that you could do some computation this way. There's another very, very important use to these types of op-amp circuits, and one that's very easy to analyze in the context of what you just learned. And that's what's called a voltage follower, or very often also called a buffer. So, and this is used extensively in integrated circuits. So consider a circuit which has a realistic input source, which is a voltage source, an ideal voltage source, and its associated resistor, and it's trying to drive a load. Okay, very simple circuit. We now know, because Vivek and I have hammered on this point several times, that the output voltage presented to the load is of course dependent on the relative values of the two resistances. And so in fact it's a voltage divider, so Vs times RL over Rs plus RL is actually the voltage you get at here, right, this expression here. And so the output depends on both the input and load resistors. This is kind of less than ideal case when driving loads, particularly when you have access to active circuits like we do.
Right. The problem with this is now the voltage that you see on your load depends strongly on the load resistance, which isn't so great.
That's right. And so what does the op-amp let us do? It lets us do something very simple. We can create a unity gain system. In other words, a system which has a gain of 1. So it's not going to amplify and multiply by some strange number or some gain as we've done before. We're going to set it purposefully to 1. So you can see here what we've done is we've just connected the input to the output. Again, it's a negative feedback configuration. But we haven't put any resistor here. And you can go ahead and solve this circuit and convince yourself that this is a unity gain. But the principal utility of this is that this essentially decouples the input side from the output side and allows us to drive loads independently of what the source resistance might be.
So let me try to see if I get that.
Sure.
So what you're saying is that this acts like a buffer. Now, I think I can kind of see that because I've got two rules that sort of help me. One is I've said Vn is going to be equal to Vp, and I've tied Vp to the output, which means if the output is therefore going to be equal to Vp. Further, since there's no current flowing into the non-inverting input, Vp is going to be equal to Vs.
That's right.
So that
Exactly right.
that's the combination that allows this to work as a buffer.
Right. And intuitively, what is going on, right? So that's the explanation with the ideal rules, which is exact. And what's going on intuitively or operationally is that this buffer is using the feedback, is pumping current so that it can supply the current that this load requires to maintain a voltage identically equal to V0, which it understands. How does it know what voltage to set? It sets it because of this feedback configuration to Vp, as Vivek said. But that's really what's happening. You have an active circuit. Remember, what we never draw, as we went through in the last module, we never draw the power supply lines. So this op-amp has rails, and those rails are providing energy, power to it. And so the buffer is essentially actively compensating so that even if this is a feeble, very high input resistance source, the load can be driven and kept at a voltage of V0.
Okay. So having done that, now we can start introducing some pretty interesting applications. For those of you who are taking these classes at Berkeley and are taking EE100 or EE43 or EE40, you will actually be possibly in your labs learning about the instrumentation amplifier. So the instrumentation amplifier is a particularly important amplifier. It's used in a lot of applications where we are trying to sense something from a high impedance input. For example, in a lot of biosensors, we will use instrumentation amplifiers, etc. So what is an instrumentation amplifier? Pretty simple. An instrumentation amplifier has two inputs, V1 and V2. The first thing, because we're driving them from a high impedance source, we buffer both the inputs. And so you'll recognize both of these set up as unity gain buffers. And then those unity gain buffers are driven into this. Michelle, do you recognize what type of circuit this is?
Well, it looks very similar to one of these op-amp configurations we did in the first 2 slides, right? Is that what you're saying?
That's right.
So my guess is this is going to be, it looks like a difference amplifier?
Yeah, and you're right, and you know that because you notice one input feeds to the non-inverting terminal, and one input feeds to the inverting terminal, and it's set up with negative feedback. So this has all, we won't actually go through the math on this one again because you already effectively done the math. It's pretty straightforward.
So what you're saying is each input is unity gained as a buffer, and then it's run through the difference amplifier we went through before. Perfect. Okay.
That's correct.
All right. So let's go through a slight variation on that, which is actually used extensively commercially, and it's available in a number of commercial packages, and it's really, really used all over the place. So we're going to take what we did in the last slide and modify it ever so slightly. So what we've done here is we've modified these 2 input stage op-amps for the 2 channels so that they in fact do have some gain. Okay? So immediately you should notice each op-amp is a negative feedback configuration, right? We flipped them so the inverting terminals are facing each other, that's all. And these 2 resistors are the feedback resistors. There's this little bit of funny business here, which we'll get to in a second, but other than that, nothing strange. And then we're feeding them straight into
a difference amplifier.
Difference amplifier, nothing fancy here. So all that's happening is we're buffering the inputs we're buffering these inputs, but we're giving them some gain, some user adjustable gain it'll turn out, and then we just take the difference and we spit that out the output. Now, the cute thing about this is really not that big a deal. We could have had 2 resistors each go to ground. So we could have had the feedback resistor, and then at this node, we could have had another resistor, call it R10 or something, that went from this node to ground, and then another resistor down here, call it R11, that went from this node to ground. And then we could have independently adjusted both of those resistors to get to set the gain for op-amp 1 and the gain for op-amp 2. But because we want this to operate as a sort of monolithic package, we want the user to have one knob and one knob only that allows it to symmetrically change the gain for both of them. Okay? And so that's why this configuration is used, and that's essentially what it accomplishes. Okay? Very often, all of these resistors are set to the same value. Okay? And in that case, the expression for the output to input transformation collapses to something very simple, which is just 1 plus 2R over R2. R2, remember, is the thing that the user gets to play with, times the difference between the 2. We're going to let you work this out, and Vivek and I will come back to it in class in office hours if we need be, but you should be able to do this. It's really just 2 amplification stages, use ideal op-amp rules for both, and then a simple difference amplifier that gives you the difference. And then this funny business here, it really falls out pretty easy. Okay, so we're going to stop here and pick up soon with a bit of a review on different types of amplifiers. Hope you enjoyed all the examples, and we'll see you in the next module.
Take care.